Hello, my name is J-Wallace, and welcome to my third physics lab, and this one is over circuits. The purpose of this lab is to examine the behavior of ohmic resistors and capacitors in parallel and in series, and then use multimeters like our ammeter or voltmeter to measure the actual volt values of conventional current and the potential differences at different points in our circuit. And then we should be able to predict the behavior of these circuits using formulas we found in class. Some requisite information, we have Ohm's law and all the ways you can reformat it. We have the node rule, which effectively says the current into a node will equal the current flowing out of a node, and also the loop rule, where the change in voltage in a closed loop, or like a circuit, the change of voltage in each part will add up to zero. And will also be needed to calculate the potential difference, which is, in our case, voltage. So first we have a simple circuit with resistors in series powered by two 1.5 volt batteries, so in total that'll be 3 volts. We can use ammeters, or we can use applications of Kirchhoff's law, which is node rule and loop rule, along with Ohm's law to calculate the current. So we don't need the ammeter, but it's useful to have to check our data. So when calculating the current at different points throughout a circuit, the first thing we want to do is find the net resistance. And because these resistors are in series, we can simply add them together. So our net resistance would be 100 plus 47, or 147. So using Ohm's law, I found the current at one ammeter using just I equals V over R, and found that the voltage was 3 volts like I previously mentioned, and we have the net resistance, which I found to be 147. So the current at one of the ammeters would be 2.04 times 10 to the negative 2. And because of a node rule, we know the current in equals the current out. So at any point, the current should be relatively consistent considering we only have a single circuit in which everything is in series. So I2 should be around I1. So my actual data, I used the circuit simulator to better represent the circuit that we made in class visually, because I found the circuit in class was kind of hard to look at. So using the circuit simulator, we can see that our data is mostly accurate. And another thing to note is that the direction you had the ammeter would also affect the sign of the current. Whether you swap the terminals or not could flip the sign, but overall the absolute values are still the same. So calculating the change in voltage at each part of the circuit is relatively easy for a simple circuit in which everything is in series. The battery induces a positive voltage of plus 3 volts, and both resistors, when added together, should induce a change of negative 3 volts if Kirchhoff's rules hold. And we can calculate this pretty simply. We can use a voltmeter, or we can see, because V equals IR, we have the voltage, or no, we have the current, which we found earlier, and the resistance of at each part. We have the resistor A and resistor B. If we add those two together, then we get 2.9988, which is very close to 3. So what this is saying is that the change in voltage from like ammeter 1 to ammeter 2 going through both resistors almost cancels out the induced voltage from the battery. And there is a minor error. Well, not really error, but there is a minor difference, and that can easily be caused by things like the wire's resistance, which we don't really calculate for. We assume a perfect wire. And also there are things like ammeters, which can induce a very small, but technically like noticeable amount of resistance. So another thing I wanted to touch on was the graph. We have a graph plotted of the voltage at location. You can see how the voltage rises to 3 and then falls back down in steps. Those steps represent each piece of resistance. You can see the smaller one is the one with the smaller resistance, and the large one is the one with the larger resistance, and it all ends up returning back to 0. I wanted to touch on is whether you use an ammeter or a voltmeter to measure in your circuit. This actually does have an effect, since a voltmeter actually incurs a high amount of resistance, meaning that when you're using a voltmeter to measure the voltage in a circuit, if you want to keep the circuit live, you should connect it in parallel. This is because if you have if the voltmeter is in parallel with high resistance, most of the electricity will still flow the intended path, versus an ammeter, which actually incurs a very low resistance. So you want it to be in series, because if it's in parallel, none of the actual current will flow through the ammeter. It's going to simply stick to the normal path of the circuit. So when you're using an ammeter, it should usually be in series, versus if you're using a voltmeter, it should be in parallel, and that will directly affect your data. So now we have a RC circuit, or a circuit with a resistor and capacitor. And so we can visualize the charging of a capacitor with a light bulb. So we have a 3-volt battery, or the same 3-volt battery, and we have a 10 ohm bulb and a 20 ohm bulb. And we saw what happens when we disconnect the battery. So when you charge a capacitor, when you just have current flowing into a capacitor, all of that charge is going to store in the capacitor, and it effectively can fuel the bulb for a short time, even after you disconnect the battery. So what we saw is that the 10 ohm bulb took about 10 seconds before it was able to fully turn off, and the 20 ohm bulb took around 20 seconds. So we can actually calculate the time it takes to charge and discharge a capacitor, and one of the interesting things about it is that the amount of time it takes for a capacitor to lose a certain amount of charge is sort of relative to the amount of remaining charge in the capacitor, so you end up with a sort of differential equation. But if you solve for it, you can end up with getting our solution, which I found to be 10 seconds and 20 seconds, which pretty accurately matched what we observed in real life. So now we can see a capacitor graph, or just like a graph of how quickly it loses charge. You can see this curve has a slope. That's because this is the difference between plotting the natural log of the graph versus plotting the graph, because it has that exponential factor of the amount of charge it loses being relative to the amount of charge it has. So this concludes my lab 3 video. Thanks for watching.